Okay, so let's continue. Okay, so we are currently on number 5. So we have b of x equals x, 12 minus 2x, 9 minus 2x. So it says it represents the volume. It represents the volume, meaning the volume is the output, with the cutout of x inches. So length of cutout. Okay. So it says, using your graphing calculator, find the size of the cutout when the volume is 35 cubic inches. So we know the output, right? So on your calculator, I know you did y1 equals this, right? So we want to know when the output is equal to 35. So we would plug that in, we'd graph it, and it looks something like this. And then say 35 was here, so these are our options. However, we're only going to be concerned about these. Why? Because this is the volume, right? So here we have a positive volume, and then here we have a negative volume. We can't have a negative volume of the box, so we're not going to be worried about that, okay? So using your intersection method on your calculator, you can find these two spots. We're looking for the size of the cutout, which is our input. So basically we know that the y's of these points are 35, right? We just want to know what these x's are. Okay, so on the calculator, it'll give you a point, and then you would just, these two x's would be your answer. Okay? All right, and it says find the maximum volume and the length of the cutout that produces the maximum volume. So we have this again. We're going to use the maximum function on the calculator. It'll give us a point, right? With an x and a y. This is our input, which is the length of the cutout. This is the volume, right? Because that's the output of our function. So it says find the maximum value for the box's volume. That would be that. What is the length of the cutout that produces this volume? That would be this. Make sense? Okay, number 6, lovely, lovely domain problems. So the 3 functions that we could encounter are polynomial, rational, and radical. Okay, so let's go over rational and radical first. So we'll start with radical. Okay, so radicals have the radical symbol. So I think of it as a person. Oh no. This is turning out so much worse than I thought it was gonna be. Okay, anyways, I don't know. I just imagined some person like standing on a surfboard or a skateboard and say, that's totally radical, dude, because this kind of reminds me of the little arm motion they make. So that's how I tell the difference between this and this, or you can just be a normal human being and memorize it, I guess. But anyways, the restriction is that this number cannot be negative, right? So if we have x plus 2, we don't want whatever's inside to be negative. So if it's not negative, that means it needs to be greater than or equal to 0. this is going to be the thing to remember for radicals. Now understand that it's only concerned with what's inside. So we're not going to do x plus 2 minus 4 is greater than or equal to 0. We're not going to do that because you're including something that's outside of the radical. We're only concerned with what's inside. So x plus 2 is greater than or equal to 0. Subtract 2 from both sides. X is greater than or equal to negative 2. And we'll go over an implementation here in a second. Okay. Rational is, think rational, fractional. Okay. Now, know that it's not just the fact that it has a fraction, but that it has our input here. So x over 2, that's not a rational. Why? Because the input is up here. So we could technically write this as 1/2 x. There's nothing that we can put in x that'll break this, so it's not a rational function. Since this is a variable, it's possible that the denominator could equal 0, right? That's where our issue is. So that's what makes this rational. So polynomial is pretty much anything that's not rational or radical. So like 1/2 x, x over 2, 2x, 4 minus 100 x cubed, da, 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 da. It can be as scary as you want. But if it's not rational or radical, it's polynomial. Okay. Going back to rational, we can't divide by 0, right? We can't do it. So, no 0 in the denominator. So we're going to take whatever's in the denominator, and we're going to say this is not equal to 0. That's the thing to remember for this one. Okay, so x, we're going to subtract 2. X doesn't equal negative 2. Okay, so let's see. Remember these two things for rational and radical. So rational functions, they're pretty rational. They only want one thing, right? They're just like, listen, I just don't want a 0 in the denominator. I could do anything else. I'm a really rational guy. That's all I want. Radical has a bit more radical of an approach, okay? It's saying, I don't want any negative numbers. So like from negative infinity to positive infinity, this guy is like, I don't want half of this. Whereas rational is a little more rational. He's saying, listen, of all the numbers, I just don't want a 0, okay? That's not too much to ask. Okay, so let's look at these problems. Okay, so she already starts you off with a tricky one. It's not that bad. I need to turn this off. Let's silence that real quick. Okay, 2x minus 10. All right, so this is a two-parter. We have a rational and a radical part. So we need to solve both restrictions. Rational and radical have restrictions. Polynomial does not. Okay, so let's look at the rational part of this. So really, anything can be on the top, right? What we're concerned about is the denominator. The denominator can't be equal to what? 0. So 2x minus 10 doesn't equal 0. 2x doesn't equal 10. X doesn't equal 5. Okay. Whenever you get these domain problems, just please do a number line, okay? So it can equal 5, right? So it can be everything before, it can be everything after. So we have negative infinity to 5, but we don't include 5, 5, positive infinity. Now, this is if it was just like 2x squared over 2x minus 10, that would be the domain, because the only rule that could possibly be broken is the denominator rule. But we're not done yet, right? But it's important to note that this is how the interval notation of the domain would look like for that kind of problem. So we figured that out. Now we need to look at the radical part of it. So we don't want negatives in here, right? So whatever is in here must be greater than or equal to 0. So notice we've been using the same things. Okay. Plus 3, so x must be greater than or equal to 3. Okay? So let's remember that. X can't equal 5 and x must be greater than or equal to 3. So let's look at our number lines again. So x can't equal 5. It can be anything before. It can be anything after. This says it can equal 3, but it needs to be greater than 3 as well. So now we need to combine these two so everyone's happy. So first, can it be anything before 5? No, it can't. Oh my goodness, I'm so tired, guys. I'm sorry. Let's try that one more time. If I had time, I would remake this video. Okay. It can be anything but 5. It can be anything that's greater than or equal to 3. Okay. Here, we have to draw a line. Because according to this, it can't be less than 3. Even though anything less than 3 makes this rule happy, it doesn't make this rule happy, and we need to make sure that both are happy, okay? So now we could think of our new number line as looking something like this. Okay, but it also can't equal 5, right? So now, does this make both rules happy? Yes. We're greater than 3, it can be equal to 3, but it still can't equal 5. So, let's do this. We are starting at 3. It is included, so we're going to use those brackets. And we're going to go all the way over to 5. But we're not going to include 5. We're not done yet, so we're going to unite this with starting at 5, but not including it, all the way to positive infinity. Okay? Makes sense? Cool. So let's look at this one. Okay, so this is a rational function, right? So the denominator can't equal 0. We're multiplying two numbers, so that means if this is 0, this whole thing is going to be 0. If this is 0, this whole thing is going to be 0. So we need to kind of split it up and make sure that neither of these can be 0. So we say x minus 4 doesn't equal 0, x minus 6 doesn't equal 0. We're going to solve. So here are 2 rules that we need to follow, right? So let's start with this. It can't be 4, it can be anything before, it can be anything after. It can't be 6, it could be anything before, it could be anything after. So now we need to combine these 2. So far it could be anything before 4, so we're okay. However, this rule says that it can't be 4. Now we go on, both of these rules say it's okay to have stuff between 4 and 6, but this rule says that we can't have anything at 6. And then these 2 rules say we can have anything after. So negative infinity to 4, not included, plus anything between 4 and 6, not included, plus anything after 6. Okay. Last one, pretty easy. Is it irrational? No. Even if it was x4 plus 6 over 3, because the x is not in the denominator, this would not be considered rational. Is it radical? No, because we don't see a root, right? So since it's not rational and it's not radical, it doesn't have any restrictions. Okay, so it's happy. So since it has no restrictions, it can be any number, meaning it can go from negative infinity, that's a terrible infinity, but that's okay, to positive infinity. All right, and we will continue this later.